Okay. What about this curve over here? Whatever it looks like, I'm gonna draw it. Just act like we don't know what it looks like though, okay? We draw it. What can you tell me about the point there? The y-coordinate is y, and the x-coordinate is y to the fourth. Do you see that it's backwards? This right here, y is what's being plugged in, y to the fourth is what the x-coordinate is. Yes? Here, this one, if I were to graph that, whatever it looks like, pick a point off there, it would be the y-coordinate is y, the x-coordinate is square root of 2 minus y. So y'all see the difference between this and this. Here the x-coordinate is just the input, the y-coordinate is the function. Here, the y-coordinate is the input, the x-coordinate is the function. Yes? Okay. On your calculators, I want you to go find on your calculator a button called mode. Go find your mode function or mode key. And then somewhere in that menu, you have an option of how to graph things, and you should have an option of function, para, polar, something like that. You all see that? I want you to go to para. What it stands for is parametric. Okay? Got it? Now, go back. Everyone got to the para? Yes? Go back to graph something now. Like if you're, go to the y equals to graph something. And what you're going to see there is this. You're going to see something like x1t, y1t, or something like that. Y'all see that? And then it'll say x2t, y2t. All right, here's what we're going to do first. We're going to graph this parabola. The way parametric works is that you are controlling the variable t. And you can control it however you want to control it. So for here, I want this to be t and this to be t squared. So I want the x-coordinate to be t and the y-coordinate to be t squared. And then here on the second one, I want the x-coordinate to be t and the y-coordinate to be sine t. So I'm basically doing this, I'm about to graph this. T squared, t, sine t. Do that and hit graph, and it's probably not going to show you the whole graph. Does it show part of it though? Okay, there should be a window key. Hit your window key. And it on the window, you should see like T-min, T-max. Do you see that? T-min, T-max? The default setting for your calculator is 0 to 2 pi, because most parametric equations involve trig functions. But for us, we're going to change the T-min to -10 and T-max to +10. And then hit graph again. And it should draw the same picture you had earlier, right? Does it draw the parabola and the sine? Yes? No? Yeah? Okay. Good? All right, go back to this now and clear these out. Clear these out. And now what we're going to do is we're going to graph this. So how would you graph this one on your using your calculator? How would you graph this one? What would your x1t be? What would your y1t be? So what would your x1t be? We're trying to graph this one right here. So which one is the input? The y value, right? So I want my y value to be t. And I want my x value to be t to the fourth. Do you see the difference? My y value to be t, my x value to be t to the fourth. And then do this one as well. Let's see, what would this one become? x2t, y2t. So here again, the y value is just t, and the x value is the square root of 2 minus t. If you do that and hit graph, you will have your graph. On Desmos, you can do parametrics as well, but I don't quite remember how, so let me just try it real quick. I think I use a brace and go t comma t squared. No?
You can plug in the actual functions themselves, and then you can use brackets to set your limits as to where and when they begin.
Yeah, but I'm saying it's not taking the bracket for parametric. Maybe it's parenthesis. It's parenthesis. Okay, there we go. So that's what I just did here in Desmos. I typed in t squared, and it graphed me part of the parabola because t is between 0 and 1. So if I change it -10 to 10, draws me the parabola. But notice if I flip it and I do it the other way around, I do t squared comma t and let t go from -10 to 10. Do you see it draws me the parabola the other way? So the blue one, oh sorry, let me say it this way. The red one, right? The red one is y equals x squared. The blue one is x equals y squared, right? So I've shared something very powerful with you just now. The parametric mode on your calculator allows you to graph functions of x and functions of y, right? Lets you do both of them. But you have to play this game of where to put t. Anytime you're doing a function of x, like traditional functions you've done your whole life, you'll always let the x coordinate be the t, and the y coordinate will be the function you're trying to graph. If you're doing a function of y, it's the other way around. The y coordinate will be t, and the x coordinate will be the function that you're trying to graph. Pretty cool, huh? You didn't know you had that power, did you? All right, so the whole idea of this was we need to know what that graph looks like, right? So now we do know what it looks like. I'm going to go to the graph. Here's the graph. Does your graph look something like this? Or can you see the region? It actually should have looked like this. And then the other one, yeah, it just does that, right? That's all it does. And then I put here y greater than or equal to 0. Yeah, which means everything above the y-axis, right? You know, I've screwed this picture up. There, it's that. So it's that region. Do y'all have questions? Is this confusing? Are you okay? What kind of rectangles do you want to use, vertical or horizontal? Look at the region. What's that? Horizontal, right? Because if you use horizontal, you never have to change anything, right? Imagine a rectangle in here that's horizontal. The curve on the right is always the same. The curve on the left is always the same. If you do vertical, it switches right here. You'll have two different curves, so we don't want to mess with that. Are these both solved for x? They are, right? So do you know which one's which? I'm going to draw this picture. We have this, and we have this. So the one on the right, this one is, which one? This one right here, right? So this is x equals square root of 2y. And then this one is x equals y to the fourth. So my rectangle is going to be in here like this. Are we missing anything? I mean, we have the curve on the right. We have the curve on the left. I already know how to set this up, don't I? Curve on the right minus curve on the left. What am I missing? Right here, this, right? So you can tell it goes from where? 0. Now, the top one, I'm not sure, right? I need to figure out what this point is. So I need to figure out where they hit each other, don't I? Which means I need their intersection. Their intersection, and their intersection is going to be what happens when I set them equal to one another. Ugh. Right? Now, I am okay with this. The book has this, on some of the homework problems, it has them do it, or expects you to do it this way. Some of these equations can just be solved by visual inspection. Like, I can just look at that right now and tell you that 1 is a solution. Right? Just check it. 1 to the 4th power, 2 minus 1 is 1, square root of 1 is 1. So 1 works, right? That's this answer right here. Now, the other way is to actually square both sides. But if you square both sides, what happens? Y to the 8th equals 2 minus y. How are you going to solve that? You're not. Okay, that's not a quadratic. The only way you can solve this equation, but we actually don't have a method for solving that. In Cal 1, you're taught, well, I don't know if your instructor went through it, but I know in my class, do you remember me talking about Newton's method? Using a computer algorithm to solve an equation? We could use Newton's method for this, but there's no algebraic way that we have that's easy. So really, the only way to get this is by inspection, just by visual. So this goes to 1, and we're done. How are we doing on time? 20 minutes, okay. How y'all feeling? You're going to need to practice, right? Here's a good one. Sketch the region bounded by y equals the absolute value of x, y equals x squared minus 2. And then find the area of the region between them. I don't think we need our calculators to graph this. I think we can do this without the calculator. Y equals absolute value of x. Y equals x minus 2, x squared minus 2. Start with the absolute value. Absolute value of x looks like a V, right? Very sharp corner at the origin. That's the absolute value of x. X squared minus 2, parabola. Opens up, shifted down 2. Somewhere down here, negative 2. Whatever, it goes like this. They'll hit each other eventually, right? You'll see the region bounded by them, by both of them. Okay? This is it. This is what we're looking for. This area right in here. Top to bottom. Vertical rectangles make sense, right? Vertical rectangles. So I can imagine having a rectangle in here. Hey, how about this? There's some symmetry in this problem. Do y'all see this symmetry? So instead of trying to figure out like going from here to here, why don't we just go from the origin, 0, to the right to where these hit and then double that answer? Does it seem fair to you? Okay. That seems simple. Let's find the intersection. Where do these hit each other? Can we do that by inspection, or do we need to solve? Let's see where they intersect. Where does the absolute value of x equal x squared minus 2? 2? I think 2 works, right? 2 and negative 2 work. If you do 2 here, right, 2 squared 4, 4 minus 2 is 2, absolute value 2. So by inspection, I can see that, right? So here's what I'm going to do. I'm going to do the integral. I'm going to go from 0 to 2, right? From 0 to 2. But I need to double this answer, right? So don't forget, I'm going to double this answer. Now I need the top function minus the bottom one. You have to be a little careful on this. The bottom one is the x squared minus 2, right? That's my bottom function. So I'm subtracting the bottom function, but what's the top function? It's absolute value of x, right? I agree with that. But we have not talked about the antiderivative of the absolute value of x, have we? We have not. We have avoided it, conveniently avoided it. But because we're on the right-hand side of 0, what really is this function? That's just f of x equals x, right? And then on this side, it's negative x. So if you go back to, I don't know, college algebra probably, the definition of the absolute value of x function is that it's just the x function as long as x is bigger than or equal to 0. And it's negative x if x is less than 0. So as long as you're at 0 to the right, it's just f of x equals x. If you're to the left of 0, it's just f of x equals negative x. And that's going to help me because if I'm going to start at 0 and go this way, then my top function is always just x. And so I just replace that with x.
So why do we avoid like the absolute value, the derivative?
Because it was just a little complicated. We'll do it now. Let's just finish this. Let's just say we're done here, and then I'll address it right now. Are we good with this? Yes? Okay. That's it. I'm ... You take the rest of the way. So let me address this question, this open question that we now have that has popped up here. What is the antiderivative of the absolute value of x dx? On your formula sheets, this does not appear anywhere. Right? Nowhere on your formula sheets does it give you the general antiderivative of this. All right? So maybe what we need to do is go back to Cal 1 and ask ourselves, if you take the absolute value of x, what is its derivative? So this is an open question. We don't know. Okay? But what is this? So let's remember, in Cal 1, the derivative is the slope of the tangent line, isn't it? That's all it is. So if you go and you look at this absolute value function, if you're to the right of 0, what's the slope of the tangent line? The blue curve. What's slope? Well, the function is x. What's the slope of it, though? Slope of that line? 1, right? And then over here to the left of 0, what's the slope of the blue line here? Negative 1. So the derivative of the absolute value of x is equal to 1 if x is greater than or equal to 0, and negative 1 if x is less than 0. Right? So this is just, look, we never talked about, I don't know, in your Cal 1 class, did you all ever talk about the derivative of the absolute value of x or no? No? Okay. But actually, it's a little more complicated than this because if you get the chain rule involved, now it becomes a little bit tricky. So the more technical answer is to put this. The absolute value of x over x is the answer for the derivative. Let me convince you. Give me any number, positive or negative. Give me any number. 7. Plug 7 in here. What would you get if you plug in 7? 1. 7 is bigger than 0, right? So if you plug a number bigger than 0 in here, you're going to have that number over itself. They'll both be positive, right? And you'll get a positive 1. Now give me negative 7. If you give me a number negative 7, the answer should be negative 1. But here, try negative 7 here. Negative 7 on top gives you 7. Negative 7 on the bottom gives you negative 7. 7 over negative 7 is negative 1. So this is a formula that will spit out a positive 1, right? A positive 1 if your value is greater than 0. It'll spit out negative 1 if it's less than 0. Oh, you know what? I messed up. This should not be here. Take that off. My mistake. Can't have 0. At 0, the derivative is undefined. Back in Cal 1, this is a sharp corner, right? You can't have a derivative at a corner or cusp. Okay, so because this is complicated, right? The derivative is complicated. The antiderivative is as well, all right? Which is why this saves us by going and taking half of it and only looking at this half. Then we are just looking at the x function, not the absolute value. So this still remains kind of an open question. You'd have to break it. You have to know what the domain is. If you knew what the domain is, then you could break this up. It's going to be either x or negative x. All right. I think I have another problem for you. We have 15 minutes still, plenty of time. Let me see here. This is going to be a bonus question. It's not, I'm not going to make it worth a ton, but it's a good exercise. I give you these curves, x equals sine of y, x equals cosine y equals 0, y equals 2 pi. The first two curves, sine y and cosine y, are sine and cosine functions, but they're functions of y, not functions of x. So they go like this instead of like this, right? And then y equals 0 and y equals 2 pi are horizontal lines, not vertical lines. And what I want to know is the area between them. So I'm just going to show you the quick picture. You can turn this in next time if you're interested in doing the problem. I've already shown you how to graph this on your calculator. So there's the graph right there. I want the area of that region, all of them together. So I'm going to leave you for that, leave you to that. All right? We're going to do one more. So that's a bonus question to be turned in next class if you're interested. Yes? And it's in your notes. It's example 8 in your notes for this section, if you need to go reference it again. Here's example 9. We want to find the region bounded by these curves. Y equals e to the x. Y equals 2e to the negative x plus 1. And x equals 2. So I would say that, having your calculator would be helpful here. I would expect everyone can sketch e to the x and x equals 2. Let's do those first, because those we shouldn't need a calculator for. So like e to the x looks like this. That's e to the x. X equals 2 is just a vertical line. Right, x equals 2. But what is 2e to the negative x plus 1? So do you all know what e to the negative x looks like? Yeah, it's that picture, e to the x, but what? Reflected over the y-axis. So e to the negative x actually goes like this, okay? But we're multiplying by 2, which does what to it? Stretches it vertically, and then moving the whole thing up 1. So imagine reflecting this, stretching it, and then moving the whole thing up 1. It should be something like instead of hitting here, it's going to hit here. It should go like up like that. It should go up a little faster and then, I don't know, come down like this. So I'm thinking it's this region right here. Oh no, I haven't done this problem in a while. Let me take a look. Hey, not bad. Yeah, so vertical rectangles, yeah? Do y'all see that vertical rectangles make the most sense here? Right? Anywhere I draw them, the blue one's on top, the red one's on the bottom. You know the top one, right? Top one's this one. Bottom one's this one. Right? Sorry, did I say that backwards? Top one, bottom one. Top one, bottom one. So I know my integral is going to be top one. e to the x, right? Top one minus bottom one. dx, because I have vertical rectangles. And what am I missing here? My limits, right? Now I know this is 2, right? Because I stop at 2. Really, this is the one I'm most concerned about. So you need their intersection. You need to know when e to the x equals 2e to the negative x plus 1. And I can remember this being a problem that my college algebra students did not like. Does 0 work? 0 doesn't work. 0 doesn't work here. Okay, so I'm going to help you solve this because we only have 9 minutes. I'm going to rewrite it like this, just so you can see it. Right, that's what that is. I'm going to clear fractions now. I'm going to multiply everything by e to the x, both sides of the equation. So what happens when I multiply this by e to the x? I get e to the x times itself, e to the x squared, equals, what happens when I multiply this by e to the x? Cancel, right? I just get 2, plus, what about this times e to the x? E to the x. What? What's wrong? Got it? I multiply this by e to the x, this by e to the x. Right, distribute here, here. They cancel, the 2's here, here times here is here. That is e to the x squared minus e to the x minus 2 equals 0. This is, in college algebra, what we refer to as a quadratic type. Squint your eyes. Do y'all see the quadratic in here? Do y'all see it? It's like, I'll do it with u. This is like u squared minus u minus 2 equals 0. And so it factors. It factors to be e to the x minus 2 e to the x plus 1. So you have two answers. E to the x, well, those aren't your answers. E to the x is 2. Set that equal to 0. E to the x is negative 1. So how do you solve for x? If you have e to the x is 2, how do you solve for x? Take natural log on both sides. Good. So take natural log on the left, you get x. Take natural log on the right, you get natural log of 2. Here, you're going to get x equals the natural log of negative 1, and your computer is going to give you an error because you can't plug negative 1 into a log. So that's no solution from this. So you only have one solution. The solution is natural log of 2. So this is the first time a limit of integration we've had is a weird thing. It's natural log of 2. So we go from natural log of 2 to 2. Remember, natural log of 2 is just a number, right? Yeah. Okay, so you'll find you'll distribute the negative through, you'll find the antiderivatives, you'll plug in 2, you'll plug in natural log of 2, you'll subtract, you'll get some numerical answer. All right. I think that that's it. I have here to do 1 through 19 odds. That's the instructions. Let me see what's on this. Yeah, okay. So I know it's Monday. I know you're tired. We have 5 minutes. I'm just going to show you a preview of next class, all right? I want you to see this right now before we actually get into it next time. So here's what we're going to do next class. This is going to be fun. Where is it?
How do you define fun?
Fun. Yeah, I know. All right. So do y'all see that picture there? That's basically what we did today, right? What we did today is we said if we have a curve on top and a curve on the bottom, we can draw a vertical rectangle, and we can take the sum of all those rectangles, and that'll give us the area between those two, right? Okay, so what we're going to do next class is we're going to imagine that these two curves that we have live in three-dimensional space. Okay? All right? And what we're going to do is we're going to take that curve, that rectangle that we had, and we're going to wrap it around the x-axis. And we're going to create this shape, which we will call a washer. Do y'all see that washer there? What am I stuck on? Oh, there's a little thing on the wall there. Okay, so we're going to create this washer, and then what we're going to do is, again, like we did before, we're going to imagine washers that go throughout this entire shape, from left to right. We're moving that rectangle. When we move the rectangle, it changes the shape of the washers, right? And imagine adding up the volume of each of those washers. If we do that, then what we're doing is we're actually finding the volume of this three-dimensional solid shape. Can you all see that? Can you all kind of visualize that?
Yeah.
That's what next class is about. It's called solids of revolution. Let me make that all the way dark. We are going to be able to find a way to find the volume of this weird shape. And it's all going to come from taking two curves that intersect one another and wrapping them around the x-axis. All right? Once we get that down, okay, once we figure all that shit out and we're comfortable with it, what we're going to do is this. I still have 2 minutes. Let me get this out of here. What we're going to do next is say, okay, instead of doing that, instead of taking that rectangle and wrapping it around the x-axis, what if I wrapped it around the y-axis? So what if I do this instead? And I create this thing that we call a shell. And then I imagine having all the possible shells as I move from left to right through this space. If I put them all together, where's this shell? There it is. Oh, I missed it. It's hard with there's a little bit of lag and it makes it really hard to do this. If I were to put all those together, all those shells together, I would get that shape. Do you all agree that that is not the same shape that we had when we wrapped it around the x-axis? So that has a different volume, doesn't it? I'll show you the other one again. Here's when I wrapped it around the x-axis. I got that shape. And then when we wrap it around the y-axis, we get that other shape, right? We want to be able to calculate the volumes of both of those. After we figure that out, what we're going to do, do I have it here? Hold on. Yeah. Then instead of wrapping it around the x-axis, which is this picture here, I know it's really small, but taking that's the same thing we just did in wrapping around the x-axis. We'll say, what if we wrap it around some arbitrary line, not just the x-axis, like down here, or some line that's above it? What would that look like? So I'm going to just do it here. Hold on. Washers, data washers, region. Okay, I'm wrapping it. So I know it's hard to see that, but that's the picture we had. That's a picture we had before, right? Earlier. It's like almost a little football. But that's if I wrapped it around the x-axis. If we take that region and wrap it around a line that's below, way down here, then we get this big like ring, right? Almost like a ring on your finger. And then this one would be wrapping it around a line above. It would still look like a ring. All those shapes have different volumes, don't they? We need to be able to know how to calculate the volumes. It looks harder than it is, okay? But we have a visual connection to it. At least we can see what we're trying to do. And then we do the same thing. We take that thing and wrap it around not the y-axis, but some other lines. So that's that other shape wrapped around different lines. All right, volumes, solids of volumes of revolution is what we start next class.